Hi everyone, so today we're going to work on linearization and over and under estimates. And the first thing we're going to do is actually just look at a Desmos graph. So if you guys could follow the link there, brings us to something that looks like this. So first thing you want to notice is if you just look at all three of these, right, not even looking at the functions, but looking at these three things graphed, they kind of all look like lines. Right? We got a red line, blue line, green line. So in a general sense, if you had to guess, maybe you'd say these are all linear functions. The biggest thing though is if you guys take a look at the window, look at how zoomed in I am, right? This is like 0.001, negative 0.001, really, really zoomed in. So if you take a look, you'll notice these functions are not all lines. And actually, if you zoom out, it's kind of the easier version to see it. Still kind of look like lines, right? But then you start seeing, whoa, yeah, these are not lines at all, right? Except for the blue one. The blue one is a line, but the red is a cubic and the green is a sine function. So that being said, it's just kind of interesting, right? When you zoom all the way in, probably would have guessed they're lines. When you zoom out though, you can tell that they're actually all different functions. And this is what linearization is. Linearization is basically when we have a small enough window, right? When we zoom in far enough. Yikes. There we go. Okay. We zoom in far enough, everything looks like a line to us. And for Calc, that's important. We've talked about tangent line approximations, and that's pretty much what we're going to be doing today, is talking about how linearization, aka tangent lines, is a way for us to approximate values for any function. So in a general sense, what we learned here, if you want to take a note on it, is if we use a small enough window or zoom in enough, essentially every function becomes linear, right? So if we're really zoomed in, pretty much everything looks like a line. Everything becomes a line if you zoom in far enough. So whatever you want to write down for that to remind yourself, this is where that's coming from. Okay, so like I mentioned, linearization is a lot like tangent lines. We've talked about this before. You guys have seen tangent lines. We've done it all year. Tangent lines, right, touches the graph at one point, and it's that approximation for our derivative at that point. So if we're writing a tangent line, don't forget that's y minus y1 equals m times x minus x1. Okay, and when we talk about it specifically at a point, maybe you'd rewrite it to be y minus f of a equals f prime of a, right, the derivative at a times x minus a. So this helps us find the equation of a tangent line at a point. Linearization is pretty much just taking this green, like if you were to zoom in really, really far to the green and blue, you were just looking at this space, you wouldn't be able to tell any difference between the green and the blue functions. They'd be exactly overlapping because even though the green has a curve to it, if we zoomed in super, super far, which Notability doesn't do a super good job, but it would basically look like a line to us. They would look exactly the same. So linearization is just the idea of turning a function into a line at x equals, whatever value. Okay, but I want you guys to just think about this. This is pretty much a fancy word, and you'll see it with AP, but I want you to write down, this is basically a tangent line. You've already done this before, and it's just a different wording and different vocab for it. Okay, so the only difference here, if you took this function right here, or this equation, you brought it down here, let's say you added f of a to both sides. Okay, so now it would say y equals f prime of a times x minus a plus f of a, like you're just solving for y. You replace y with L of x. This is the linearization, okay, is equal to f prime of a, x minus a plus f of a. This is technically linearization, the function that you would need to use. So if you see linearization, basically you just solve for y, replace it with L of x. But notice we've done this before. It's actually not technically new material. It's just a new way of talking about it, a new way of describing tangent lines, and then how do they relate to approximating different values as well, which we'll talk about below. So take a look. Let's try a couple examples here. Okay, so it says find the linearization of g at x equals 2. All right, so I don't want you to be confused here. Again, this really just means find the tangent line. So kind of treat it like normal. X equals 2, you have x equals 2 or y equals 10. You have a slope of 3, so you just plug that in. Y minus 10 equals the slope of 3 times x minus 2. The only weird part here, linearization just means solve for y. You can distribute the 3 or not. I'm not going to right now. Okay, and replace y with L of x. So technically your linearization, if you saw this on AP, would be something like that, L of x. They don't expect you to necessarily use L of x, but just in a general sense, if you see linearization, don't be intimidated. That just means find the tangent line. Okay, so that's linearization. Then it says approximate g of 2.1. Okay, so here's what we're thinking about for that. How can we approximate something we don't even have it, right? We have nothing about 2.1 here. Okay, what we do know, the graph, I'm just going to draw kind of a random sketch of it, but in a general sense, we know, kind of looks like this. I don't know. And if we're at 2 here, okay, let's say we had our little line of tangent line, you know, something like that. Okay, and then we also are looking for this 2.1, so super, like literally right by it. And I'm not even doing a good job justifying it. You know, that line, the point on the line would be probably a pretty good estimate. It's super close to 2, so we're going to approximate, yeah, it's probably the same thing as whatever's on that line, you know, just about. Now, obviously, it's not going to be exact, which is why it's an approximate value. So we're going to do the linearization of 2.1. That's the same thing. I guess I should put this first. G of 2.1 is approximately what happens when we plug in 3 times 2.1 minus 2 plus 10. So we're just plugging this in for x right here. Okay, so if we plug in x and we solve, okay, so L of 2.1 would be 3 times 0.1 plus 10, which is 10.3. So in a general sense, we can approximate, okay, that G of 2.1 is approximately 10.3. Now, the nice part here is you don't actually have to use L of x. You could have used this right here. We could have been doing this before, right? So what if I just did y minus 10 equals 3 times, what happens if I plug in 2.1 instead of x? If you solve this, you get 10.3. So exactly the same answer. So don't be confused that this is something crazy and new. Basically, the main goal is that you're getting 10.3 for that answer there. Okay, and then the last part is, and we've kind of talked about this briefly, but we'll show how it relates. It says, look at part B, okay, this 2.1 situation. Is it an over or under estimate? Okay, this has to do with concavity. We've talked about before, we've had questions where it said, is the tangent line above or below? So hopefully you guys remember that. So in this case, right, and you'll see why I drew it this way, okay, we know that G double prime of 2, which is concavity, is negative 5, which is less than 0. So if the second derivative is negative, that means it's concave down, which is what I drew in my little sketch, so that we could use that sketch again. Okay, it's concave down, so if I asked you guys, concave down, is the tangent line above or below? Well, you can tell right here it's above, right? Tangent line is, I should have written tangent line here. Okay, tangent line is above. Okay, so if you take a look, we're not going to say above and below. Now we're going to say over and under estimate. If we're above something, you know, that's an overestimate. But if you want to see why, it's kind of because if you can tell, this is actually the orange. Well, here, let me use a different color, this green. This is actually G of 2.1, and this is what we approximated it to be. So since the line is above, right, we were probably a slight overestimate for what G of 2.1 actually is. Okay, so our sentence here could just be something like this, or our justification. It's an overestimate. We already talked about how it's above. That's really where this is coming from. Because G of x is concave down at x equals 2, since G double prime of 2 is negative. Okay, so you don't have to say the above and below for tangent lines, since that's not what it's asking, but that is where it comes from. So since you've been practicing doing that, keep following suit. If the line's above, right, then we are overestimating the function value. All right, so we're going to try out number 2. Okay, so take a look, similar idea here. It says use a tangent line to approximate this value. Okay, so again, use a tangent line. We know how to do that. Technically, it's asking for, you know, the linearization, same meaning. We're going to approximate this, you know, doing L of 6.02 if you want to think of it that way, or plug in 6.02 for x. So we have h of 6 is 30. We need to know, you know, we could start writing this out. Y minus 30 equals whatever h prime of 6 is times x minus 6. So this guy, that slope at 6, or that derivative at 6, let's see. H prime of 6, we have h prime right there. So 6 squared over 6 plus 3. It's 36 over 9, which is 4. All right, so in a general sense, here's your tangent line. Y minus 30 equals 4 times x minus 6. Okay, and right here, you could plug in 6.02 and solve for y. That would be the exact same answer. I'll write the linearization just because we're practicing that. So remember, you add or solve for y, aka add the 30 to the other side, and you replace y with L of x. Okay, so then h of 6.02 is approximately the same as the linearization at 6.02, which is 4 times 6.02 minus 6 plus 30. Plugging into this right here. Again, you could have plugged in x right there, so if you feel like doing that, feel free. And we get, what do we get here? H of 6.02 is approximately 4 times 0.02 plus 30, so that'd be 30.08. Okay, so that's it for that one. Now this one says determine if it's an over or underestimate. So we just talked about this. Remember, over and underestimate has to do with concavity. So take a look. We're looking at 6, right? What's happening at 6? So h double prime's right there. So h double prime of 6 would be 6 squared plus 6 times 6 over 6 plus 3 squared. And honestly, guys, I'm going to be a little lazy here. The only thing we care about is that's going to be positive, right? I mean, I can see it's going to be positive 72 over 81 maybe. And either way, I don't really care what the value is. I just care that it's positive. Why? That means it's concave up, right? And that means the tangent line is going to be below, okay? Meaning, if I drew in, you know, if I was trying to approximate at 6, and then I looked at, I don't know, this should be 6. 6, and then 6.01 was right here. Okay, 6.01, I would have been a slight underestimate, okay, because, remember, this was overestimate, we were concave down, right? So tangent line was above. This one is underestimate, okay, because we're concave up. So the tangent line is below. So whatever notes you need to write there, you don't need to write much. I would say what you do need to write, obviously, is that justification, and that's it. So what is our justification? Our justification would be, it's an underestimate at x equals 6. All right, it's in from part A. At x equals 6, since h of x is concave up, you know, at x equals 6, since h double prime of 6 is positive. All right, so that is number 1 there, or number 2, oops, I should name this probably number 3. We're going to do 3A, and then I'm going to actually have you guys try 3B, but very similar situation here. So take a look. We've got negative natural log of 4x. It says use a tangent line to approximate, at x equals 5 to approximate f of 5.17. So same thing, guys. Tangent line, aka linearization if we want. Okay. Our tangent line, let's see, we need f of 5 for sure. What is the y value here? Negative ln of 4 times 5 is just negative natural log of 20. Okay, how about f prime of x, right? We need that slope at 5. Derivative of natural log is 1 over whatever's inside times derivative of what's inside. So this would give me negative 1 over x. Okay, and then we need what's the slope at 5, or what's the derivative at 5? Be negative 1/5. All right, so you have all your pieces. Again, hopefully that's kind of review. So we write our tangent line to be y minus natural log of 20. That was the y value at 5, equals the slope or the derivative at 5, negative 1/5, times x minus the x value, which is 5. All right, and again, that's the tangent line, so you could stop here in terms of finding the tangent line, or you could solve, and you could say L of x would be negative 1/5 x minus 5. That'd actually be minus natural log of 20. So up to you. Okay, and the last step here, you're either going to plug it in right here, or right there, I'll do this linearization equation. F of 5.17 is approximately L of 5.17, which is negative 1/5, 5.17 minus 5 minus natural log of 20. Okay, and either you would leave it literally like that, obviously, or you'd have a calculator. You wouldn't have to do this by hand. So I'll just give you that calculation here. 5.17 is approximately, this whole thing ends up being negative 3.030. All right, so that would be your answer there. Okay, so I want you guys to actually try out part B. Okay, you're going to answer the question here on the video. Now it says over or under estimate, you need to look at concavity, right? That's what we talked about. Concavity has to do with the second derivative. And if you have the first derivative, how can you get to the second derivative? So I'll let you guys try that. You should write out that justification as best you can. And we'll go over it in class. So let me know if you have any questions, and thanks so much for watching.